Hello everyone, this is the talk for the paper A Faster Algorithm for Finding Tarsky Fixed Points, and I'm John Fearnley, and this is joint work with my co-author Rahul Savani, and we're both from the University of Liverpool. So I'll start the talk by defining the problem we're interested in, and we're interested in the Tarsky fixed point problem. So what is that problem? So it's defined over a lattice. Tarsky's fixed point theorem is defined over a lattice, and for this particular line of work and all the work that's been done on Tarsky's fixed point theorem, or at least the complexity of it, has been done over the integer grid lattice. So we have integers between 0 and n in a grid. So here we have a two-dimensional grid, but more generally we imagine a higher dimensional grid of dimension k containing integers between 0 and n. Then, given such a grid, you can define a natural partial order over the points in that grid. So here we have a point x, and we're just going to use element-wise comparison. So a point is less than this point x if all of its coordinates are less than or equal to the point x, and a point is greater than the point x if all of its coordinates are greater than or equal to the point x. And that means, of course, there are some points, like points up here and points down here, that are actually incomparable to x. So this has one coordinate greater and one lesser, which means it cannot be compared to x. So that's the definition of our partial order. And then we have this definition that's necessary for Tarsky's theorem of order preservation. So what does order preservation say? It says if I take some function that maps the lattice to itself, so it takes input, points from the lattice, and as output gives points in the lattice, then that function is order preserving if, whenever x is less than y, we have that f of x is less than f of y. So here we've just drawn some possible values for x. The arrow means that the function f, if you give it this point, will output that point, and if you give it this point, will output that point. And we can see that these arrows satisfy order preservation. So if this was x and this is y, then we have that x is less than y, and f of x is less than f of y. These were a, b, and c. We have that a is less than b is less than c, and f of a is less than f of b less than f of c. And one thing to note is this only bites you in the case where x is less than y. If x is not less than y, then there is no constraint at all. So here we have that x is not comparable to a, b, or c, and we can see that f of a is less than f of x, f of b is incomparable to f of x, f of c is greater than f of x. That's all fine. Order preservation just says if x is less than y, then f of x must be less than f of y. If that's not the case, then it doesn't matter what the relationship between f of x and f of y is. So that is the definition of order preservation. And now we can define Tarsky's fixed point theorem. The Tarsky's fixed point theorem says every order preserving function on a complete lattice has a fixed point. That means if you give me an f defining this lattice that is order preserving, then there is some point in this lattice such that f maps that point to itself. So this could be x, and we can see that f of x is also x. So that is a fixed point, and Tarsky's fixed point theorem says so long as you are order preserving, there must exist at least one fixed point somewhere in the lattice. And actually it says something quite stronger. If you go to Tarsky's original results, so Tarsky actually proved that every order preserving function on a complete lattice has a greatest and a least fixed point. So actually all the fixed points themselves are partially ordered, and there is some fixed point that is actually below every other fixed point. If the red dots here are indicating points that are fixed points, this guy is the least fixed point, and this guy is greater than all the other fixed points, so he is the greatest fixed point. So the weak version says that there's at least one fixed point. The stronger version says that not only is there one fixed point, there is also a least one and a greatest one. So given Tarsky's fixed point theorem, you can now actually define a computational problem we will call the Tarsky problem. So you actually presented f, and here we're going to assume, in this paper, we're going to assume that f is an oracle, and we're going to make queries to it. We could equally well assume that f is some function defined by a circuit that you can actually inspect if you want, but we're going to do the query complexity point of view in this paper. So you're presented f, and you're asked to find, okay, either find me an x that is a fixed point, so an x such that f of x is equal to x, or, now, obviously, if f is order preserving, then a fixed point will exist, but given f, you have no way of knowing if it is order preserving. So to cover that case, we say, okay, either find me a fixed point or find me this second thing, and this second thing is a violation of order preservation. So order preservation says if x is less than y, f of x must be less than f of y. So if you can find me an x and a y such that x is less than y and f of x is not less than f of y, that's a violation of order preservation. That means Tarsky's theorem doesn't hold, and so there may actually not be a fixed point to find in that instance. So we're saying, if it is order preserving, find me a fixed point. If it's not order preserving, either find me a fixed point which might still exist, or find me a violation of order preservation, which must exist because it's not order preserving. So that's the Tarsky problem. And by Tarsky's theorem, actually this problem lies in a complexity class called TFNP. If you've never heard of it before, what is this? This is the class of function problems that are always guaranteed to have a solution. So it's not a decision problem. We're not asking for a yes-no answer here. We're saying, given this f, actually find me the point that is a fixed point, or find me 2 points that are violations of order preservation. So it's a function problem because we're asking you to actually find a point or 2 points, not make a decision yes or no. And it's total. This T says it's a total function problem because it always has a solution. And we know it always has a solution because of Tarsky's theorem. So Tarsky's theorem says if you are order preserving, then there is a fixed point. And if you are not order preserving, well, then there must be a violation of order preservation. So no matter what f you give me, there is definitely one of these two things that you can find, or that I can find, to give you back in order to solve this problem. So it's a total function problem, and then this NP just says it's in NP, meaning that we can efficiently verify the solutions to the problem. So if you give me a fixed point, I can verify it's a fixed point. If you give me an order preservation violation, I can verify it's an order preservation violation, both in polynomial time. I just need to inspect what f does to these 2 points. So it's in TFNP, and actually, it's actually in, so TFNP has been fairly well studied over the last 30 years or so, and there are known kind of subclasses of TFNP that are more constrained. So these are total problems of certain formats, and you may or may not have heard of classes like PPAD and PLS, but they're probably two of the most famous TFNP subclasses, and it turns out that this Tarsky problem lies in both PPAD and PLS. That was shown in 2020, so just last year. And then more relevantly for this paper is studying the query complexity of the problem. And so this there is a known algorithm to solve the Tarsky problem given by Dang, Chi, and Ye back in 2012. So if the lattice has width n and dimensionality k, their algorithm runs in log to the power of k n time. So it's logarithmic in n, but then you raise the log n to the power k. So this is actually an exponential time algorithm. It's much, much better than brute force. Brute force would be n power k to enumerate all points in the grid. So here we're saying we can do it substantially faster than brute force. So log n power k. But of course, it's still exponential in the number of dimensions. So that is, before this paper, the best known algorithm for solving the Tarsky problem. And this is a query complexity algorithm. So we measure this log to the kn is the number of queries we need to make to f in order to actually find one of these two things. So some other things that are known, so that's the upper bounds, upper bounds for the Tarsky problem, how quickly can we solve it? In terms of lower bounds, the first thing that should be pointed out is if you're looking for the greatest or least fixed point, which are guaranteed to exist, but they are actually much, much harder to find than any fixed point. So finding any fixed point is in PPAD and PLS, but finding the greatest or the least fixed point is actually already NP hard. This was shown by Etisami, Papadimitriou, Rubinstein, and Yannikakis back in 2020. And that holds even in one-dimensional instances. So it's very, very difficult to find the greatest or least. And in this paper, we're looking for any fixed point, not necessarily the greatest or the least fixed point. And actually, relevant for this paper, also shown by these guys in 2020, is that query complexity lower bounds have been shown in 2 dimensions. So in 2 dimensions, log squared n queries are required. And if we just go back and look at that upper bound, that exactly matches the upper bound of Dang, Ji, and Ye. So they have a log to the kn query upper bound. K is 2 in 2 dimensions, so that's log squared n upper bound. We have a matching log squared n lower bound for 2 dimensions. So then the starting point of myself and Rahul looking at this problem was, okay, we have this lower bound in 2 dimensions. Kind of the obvious thing to do would be to extend the lower bound to higher dimensions. So we know that the query complexity of Tarsky in 2 dimensions is theta log squared n. Does that mean that, or can we extend that lower bound to show that the k-dimensional problem has theta log to the kn query complexity? So it's a very attractive kind of hypothesis, and we did indeed spend quite a bit of time trying to prove this, and we were quite surprised to find out that that is not the case. So what we showed, and the main results of this paper, is that 3-dimensional Tarsky can also be solved in log squared n queries. So the previous algorithm would run in log cubed n queries, and we're running in log squared n, so we're saving a factor of log n to solve the 3-dimensional problem. And in fact, the 3-dimensional problem has exactly the same query complexity as the 2-dimensional problem, quite unexpectedly. And then this, okay, given that you have a new algorithm for 3 dimensions, you can then use that algorithm to solve all higher dimension problems faster, because already this Dang-Chi-Ye algorithm is recursive, and so you just plug in our new faster algorithm for 3 dimensions into their recursion, and you very quickly get a log to the k-1 n query algorithm for the Tarsky problem in k dimensions. So certainly we now know that the k-dimensional Tarsky problem does not have log power kn query complexity, and that is really the main kind of outcome of our paper. So in terms of this talk, what am I going to tell you about? I'm going to tell you a little bit about how our new algorithm works, and I'm actually going to contrast it with how the previous algorithm works. I'm going to tell you a little bit about how the algorithm of Dang, Ji, and Ye actually works. And I'm going to say essentially how we improved upon that result to get to lose this factor of log n for the 3-dimensional case. So we're going to start by looking at this algorithm of Dang, Ji, and Ye. So how exactly do we find a fixed point of a 2-dimensional instance, or indeed any dimensional instance? We start just by giving a couple of definitions. So I'm going to define a set of points called the upset, and the upset contains every point that moves up according to the partial order. So if x is less than or equal to f of x, then x is in the upset, and we can see here these 3 points, f is moving them, but all the time they're moving them up. So these are in the upset, and symmetrically, the point x is in the downset if f moves you downwards. So if f of x is less than or equal to x, then you're in the downset. And note that not every point is going to be in the up or the downset, because there's no requirement that x should be comparable to f of x. If I was a point up here and I was moving down and to the right, I wouldn't be comparable to f of x, and so I'd neither be in the up or the downset. We know the up and down sets are non-empty because the least element has to be in the upset because it's got nowhere to go but up, and the greatest element of the lattice has to be in the downset because it has nowhere to go but down. And actually, so a fixed point, obviously a fixed point is a point such that x is equal to f of x, and that means, if we just look at the definitions, these are weak inequalities. That means every fixed point is in both the up and the downset. In fact, the intersection of the up and the down set is exactly the set of fixed points. And so to give a very broad diagram of what a Tarsky instance actually looks like, we kind of have this upset, we have the down set, and we have this region where the up and the down set overlap. Not every point is in the up or the down set. And we know that the upset kind of starts at the least element and goes upwards, and the down set starts at the greatest element and goes downwards. And indeed, you can actually, Tarsky proved that the greatest fixed point is actually the largest point in the upset, and the least fixed point is the least point in the downset. And one important property we're going to use here in this paper, which I'm not going to prove, but you can prove, is that if I give you a point in the upset, and I give you a point in the downset, so x is a point in the upset, y is a point in the downset, and x is less than y, so x might be here, y might be up here, then we know somewhere in between those 2 points there must exist a fixed point. And actually, all the algorithms we're going to see are going to really use that property to zoom in on fixed points, which we'll see in a little bit. So now coming back to the algorithm of Dang, Qi, and Ye, how do they find a fixed point in a two-dimensional instance? Well, what they do is they pick out a one-dimensional sub-instance of this two instance. So that corresponds to just fixing a line somewhere in your instance. And actually, I'm not going to go into the details here due to time constraints, but on a 1D Tarsky instance, you can very easily find a fixed point in log n queries just by applying binary search. So what does that mean? You're looking on this line, and you're looking for a fixed point of the 1D instance, and the 1D instance only cares about whether you're going left or right. So that means you find this point, and it's a fixed point in 1D, so it's not going left, it's not going right, but f could move this point upwards, and f could move this point downwards. So it's not a fixed point in the 2D instance, but it is a fixed point of this 1D instance. Now we bring this point out, and we look what's going on in 2 dimensions. We look where f moves this point in 2 dimensions. We know it's not going left, we know it's not going right, but it could be going up, or it could be going down, or it could be not moving. Now one observation is, okay, given that it's not moving left or right, if f moves this thing directly upwards, then we have that x is less than f of x, meaning that x is in the upset. Conversely, if this arrow was pointing downwards, then x would be bigger than f of x, and so x would be in the downset. And if we get really lucky, maybe x doesn't move at all, in which case x is already a 2-dimensional fixed point, and we're really happy because that's what we were looking for to begin with. But let's assume we don't get lucky, and we get that x is in the upset, so x is moving strictly up and is in the upset. Well, now I can actually rule out 3 quadrants of my instance. Why can I do that? Because let's remember that property, if I have a point in the upset, which is this point here, and I have a point in the downset, which in this case is the greatest element, which is in the downset, then I know there is a fixed point somewhere between this point and this point, which means there must be a fixed point up here, which means I can delete these 3 corners of my instance, just focusing on this sub-instance, and then I know I haven't thrown away all possible solutions. And if instead I got a downset arrow here, then I'd rule out this quadrant, and this quadrant, and zoom in on the lower left. So we rule out at least half of the remaining space. Here it was 3/4, but we don't have any control over where this point we get back from the recursion actually is. So it could be all the way over to the left, in which case we'd only rule out the bottom half, but we're still ruling out half the instance, which means we can continue on the remaining half. And since we were ruling out half the instance each time, for 2 dimensions, we get a log squared n query algorithm. Why is that? Because each time we solve a 1D instance, we're applying binary search, which requires log n queries. And we do that log n times because we rule out half the instance. And so it takes us log n times kind of outer queries to get us down to a small enough instance. So this is a log squared n algorithm in 2D. And using the same idea of, okay, I'm in 3D, I'll take a 2-dimensional subinstance, recursively find a fixed point, then zoom out. You can essentially use this technique to solve k-dimensional instances in log to the kn time. Every time you add a new dimension, you just add log n in multiplying your query complexity. So that's the algorithm of Dang, Qi, and Ye in 2 dimensions. Now let's talk about 3-dimensional instances, what the Dang, Qi, Ye algorithm actually does, and how we have improved upon it. So we've seen kind of the scheme that Dang, Qi, and Ye actually do. They fix, in 2D, they fix a line, a 1-dimensional line. In 3D, they would fix a 2-dimensional slice of this 3-dimensional instance, and then they would recursively solve, find a fixed point of this 2D instance. So it's not moving left or right, it's not moving up or down, but it could be going into the slides or out of the slides. They find this fixed point, and that, of course, takes log squared n queries. And then they look in the 3rd dimension, are we going up, are we going down? If we're going up, we're in the upset, meaning there is a solution between P and the greatest element, so I can actually throw away, I can keep just the top right back subcube and throw away the rest. If we get we're coming out of the slides, then I can keep just the front left bottom subcube and throw away the rest. And of course, here we got lucky where P was roughly in the middle, but if P was down here in a corner, we'd actually just throw away the front face and recurse on the back face. So that's their algorithm. And In the worst case, it throws away half the cube each time, meaning you need log n iterations. In 3D, each of those iterations recursively solves a 2D slice in that 3D cube. That requires log squared, and so you get log n times log squared, giving you log cubed n queries in total. And the way they're doing it, it seems like you can't really do any faster using this idea of finding a fixed point of a slice, because we actually know from that lower bound that finding a fixed point of a 2D Tarsky instance requires log squared n queries. So it seems like you're going to get log n times log squared n equals log cubed n due to that lower bound. So how do we actually get around this? Well, we do something similar. We take a 3D instance, we focus on a 2D slice, but we don't look for a fixed point of that slice. We look for something a little bit more general. So the argument here for throwing things away only cared about whether this point P we got back from the 2D slice was in the up or the down sets. Now, one way of making sure it's in the up or the down sets is to find a fixed point, and then it has to be either up or down or fixed. But you don't need to find a fixed point necessarily to find a point that's in the up set or a point that's in the down set. So that's what we actually do. The key difference between us and the previous work is we don't look for a fixed point of this 2D slice. We look for any point in this 2D slice that is in the up or the down set. And given that, you can use exactly the same reasoning to rule out the first half of the cube or the second half of the cube or whatever. You can still cut off at least half of the cube, but you're looking for now not a fixed point, but something in a bigger set of points. Because we know the fixed points are in the up and the down sets, but I'm willing to accept from this any point that's in the up or the down set, which is, so they're looking for something that's not moving left or right, or up or down. We will accept something that moves right and up and into the slides. That's all fine, so long as it is in the up set. And then what is the actual kind of punchline? The punchline is you can actually find these points faster than you can find fixed points. Finding a fixed point in a 2D instance requires log squared n queries. We give an algorithm to find one of these points that runs in log n queries. And of course, so they get log n times log squared n, we get log n times log n, and so the overall running time of our algorithm is log squared n queries in total. And so the main technical meat of the paper is in fact this new algorithm that finds an up or down set points in a 2D slice in log n queries. Unfortunately, due to time constraints, I can't really go through the meat of that, but I can give you an idea of kind of the ideas behind it. So we have our 2D slice, and this is in a 3D instance, and we're looking for these up or down set points. And the idea is, okay, we're just going to query the middle somewhere, and then we're going to do a case analysis based on what we got back from that middle query of the slice. And it turns out that in some cases, using a few extra queries, you can, no matter what you get back from this middle query, there are actually 6 different possibilities, you can rule out at least half of the slice and recurse on the remaining space. Indeed, there are 6 queries, and indeed the slides that we have here are actually less complicated than the actual thing in the paper, because in the actual thing in the paper we have some additional bookkeeping to do, which leads to actually quite a few more cases. But the punchline is, kind of the broad idea is you make a query in the middle on the midpoints, you do a few extra queries, possibly to do some bookkeeping along the way, but then using that constantly many queries, you can rule out at least half of the space and find this thing. So the theorem is, given a 2D slice of a 3D instance, a point in the up or down set can be found in log n queries. You then plug that into the outer algorithm, which will then give you a log squared n algorithm in total. So that's the main technical results. One consequence of that is actually we get faster algorithms for all dimensions of Tarsky instances. So the Dang algorithm, the Dang et al. Algorithm is a recursive algorithm. We've seen that you solve a k-dimensional instance by making log n queries to k-1 dimensional instances. And so we can just plug in our faster log squared n algorithm into that recursion, and then it immediately gives us this theorem. So for k greater than or equal to 3, the Tarsky problem can be solved using log to the k-1 n queries, which is strictly faster than log to the kn queries, which previously, at least we hypothesized, might actually be the query complexity of Tarsky. So, what are the open questions arising from this work? I think the main open question is, what on earth is the query complexity of the Tarsky problem? So, defying expectations, at least our expectations, we thought it was log to the kn before we kind of disproved ourselves. It is not theta log to the kn. So, whereas life was perhaps fairly simple before, and we just need to show this lower bound to match the known upper bounds, now things are a bit more complicated. We know it's somewhere between the upper bound of log to the k minus 1n, and the only non-trivial lower bound we have is this log squared n lower bound for 2 dimensions, which also applies to higher dimensions as well. So it's somewhere between k minus 1 and 2, and obviously further research is going to be needed to close that gap. So a couple of possible directions. These are just speculative. Perhaps the query complexity is still kind of linear. The exponent is still linear in k, so perhaps it's k over 2 or k over 4, in which case can we show such a lower bound? Or perhaps, to be consistent with this lower bound, perhaps actually it's not exponential in k, and it's some constant that depends on k multiplied by log squared n. That's still consistent with our known lower bounds, so perhaps that could be the case. There's a huge range of possibilities out there, and we're really going to have to work harder to figure out the true answer here. And we haven't really spoken about computational complexity, but I think the computational complexity of the Tarsky problem is also a very interesting open problem. As I mentioned, it's known to be in these complexity classes PPAD and PLS, but there is no known polynomial time algorithm for solving these problems, so it's not known to be in P. So is it complete for some complexity class that is thought to be higher than P? So one actually kind of obvious route is actually PPAD in PLS unexpectedly recently was found to actually contain non-trivial complete problems. That was shown actually by myself, Paul Goldberg, Alexandros Hollander, and Rahul Savani, also on this paper. So this complexity class has complete problems, and perhaps Tarsky, which lies in both of them, could be another such example of a PPAD intersect PLS complete problem. So that is a future work, therefore, for finding the computational complexity of the Tarsky problem. Okay, that brings us to the end of the talk. Thanks for watching this far. If you do have any questions about any of this, we're happy to talk to you about it. So please do just drop us an email. This is the email addresses for both me and Rahul. We're happy to discuss anything arising from this paper. If not, then thanks for coming, and see you around.